f of z equals u plus iv is analytic. Show that del square modulus of f of z whole square equals 4 times modulus of f dash of z whole square. We know that del square is the Laplacian operator whose expansion is del square equals dou square by dou x square plus dou square by dou y square. So here we have to evaluate dou square by dou x square plus dou square by dou y square upon modulus of f of z the whole square. So we first evaluate what is modulus of f of z. We know that for a complex number, modulus of the complex number is square root of sum of squares of real and imaginary parts. Hence, when f of z equals u plus iv, we have modulus of f of z equals root of u square plus v square. Now we evaluate dou by dou x of modulus of f of z the whole square, which is dou by dou x of u square plus v square. Since u and v are functions of x and y, partial derivative of u square with respect to x will give you the term 2u into dou u by dou x. Partial derivative of v square with respect to x will give you the term 2v into dou v by dou x. Similarly, when you carry out partial differentiation of modulus of f of z the whole square with respect to y, you have the terms 2u into dou u by dou y plus 2v into dou v by dou y. Since we are looking for the expression of Laplacian operator operated over modulus of f of z the whole square, we again have to take dou by dou x of this answer and dou by dou y of this answer so as to get the expansion of del square. When we evaluate dou square by dou x square of modulus of f of z the whole square, we will be operating dou by dou x on the RHS of equation 1. Note that when we operate dou by dou x on RHS of equation 1, we will have to make use of product rule because u and dou u by dou x involves terms of x, v and dou v by dou x also involves terms of x. So we will have to make use of product rule. Similar for the case when we evaluate dou square by dou y square of modulus of f of z the whole square, we operate dou by dou y on the RHS of equation 2. When again we have to use product rule on both the terms because u and dou u by dou y might involve terms containing y, v and dou v by dou y also might contain terms involving y. After application of product rule, we are expecting 2 terms from here and 2 terms from here. So in total we will have 4 terms once product rule is applied to evaluate dou by dou x applied on this term. Similarly, when we apply dou by dou y on the RHS of equation 2, we are expecting 4 terms after application of product rule of differentiation. 2 is common to all the terms when we try to apply product rule on the RHS of equation 1. When you apply product rule with respect to x over the term u into dou u by dou x, you have the first term u into dou square u by dou x square plus dou u by dou x into dou u by dou x, which becomes dou u by dou x the whole square. Similarly, when you apply product rule on v into dou v by dou x, we have v into dou square v by dou x square plus dou v by dou y into dou v by dou y. In similar fashion, we get terms for dou square by dou y square applied on modulus of f of z the whole square. We are looking for the expression of del square applied on modulus of f of z the whole square. So we will have to add up LHS of 3 and 4 together as well as the RHS of equations 3 and 4 together. Adding equations 3 and 4, we notice that 2 is common to all the terms in the RHS. Also, we group terms containing u, terms containing v, and also we separate the groups which do not involve v and u. We see that when we group terms containing u, we obtain dou square u by dou x square plus dou square u by dou y square, which becomes 0 because u is the real part of analytic function f of z and u is harmonic, hence u satisfies Laplace equation. So this particular term will become 0. Similarly, when terms containing v are grouped, we obtain dou square v by dou x square plus dou square v by dou y square, which also becomes 0 because v is the imaginary part of an analytic function. Hence v will be harmonic function as well, and hence v satisfies Laplace equation. So we are left with only 4 terms which are partial derivatives and the square of the partial derivative. Once we have applied Laplace equation, we are left with partial derivatives of first order, and all the terms are actually squares of partial derivatives of first order. Since f of z is analytic function, we can make use of CR equations. Ux and Vy are the same, and Vx and minus of Uy are the same. Hence we have 2 times ux the whole square plus 2 times vx the whole square. 2 can also be taken outside. Thus we obtain the expression del square applied on modulus of f of z the whole square equals 4 times ux square plus vx square. We number it as equation 5. Since f of z is an analytic function and f of z equals u plus iv, we have f dash of z equals ux plus I times vx. When we take modulus of f dash of z, we have square root of sum of squares of real and imaginary parts of f dash of z. Thus we obtain f dash of z the whole square equals ux the whole square plus uy the whole square. Number it as equation 6. Looking at equation 5 and 6, we obtain the desired result. Del square applied on modulus of f of z the whole square equals 4 times modulus of f dash of z the whole square.